Makarand?
Good afternoon, sir. Mm.
So do you have any question or about either assignments or about the course?
No, sir. I just joined the meeting to see like other people have any questions.
Okay, sure.
Mm. Mm.
You can wait for a little while because you are the first person to have joined.
Okay, sir. Fine.
Where are you from, Makarand?
I'm from Hyderabad, sir. Like,
Okay.
I met you at the INACOM conference thing.
Oh,
Mm.
yes. I don't remember your voice.
Mm.
Okay, so there is a question from Mr. Ravi Tiwari. Okay, what will be the correct control technique while controlling a robot manipulator attached to load via flexible connections? Example, exoskeleton. Is it possible to have force control at the tip of end effector for one task? Use null space where joint rotation does not affect end effector for few joints to achieve different tasks. Okay, so I think the first question is what will be the correct control technique while controlling a robotic manipulator attached to a load via flexible connection? Okay, so this is a topic. I mean, it's a basically if you want to do position control, then it is possible. Okay, so position control of a flexible robot is a very well studied problem. So it is much, much harder than controlling a robot which is not flexible. Okay. So it's a little bit outside the scope of this course, but if you write to me, I will send you a lot of literature details. Okay, so it's also there have been students of mine who have done of modeling and control of flexible robots. So not directly connected to your exoskeleton, but basic techniques are all there in these papers which were done long time back. There is also a chapter in my book, okay, which gives lot of details about how to control a flexible robot. Okay, so the basic idea is that once you start moving, it will bend. When you come to a stop at the desired location, it will start to vibrate. So the question is, how do you ensure that you come to stop at the correct place without vibrating? So that is what is position control. Okay. So force control is also much hard. It is not, most of the time it is not possible. Okay, you can think of it that if you want to apply a force with your robot which is flexible, then the robot itself will bend and you don't know how much it will bend. So that is a very complicated topic. So depending on how much flexibility is there in the links and in the joints, you may be able to apply some force, but it is very, very complicated. Okay, so that was question one. Second question is it possible to have force control at the tip of end effector for one task and use of null space for few joints to achieve a different task? Okay. So if I understand your question, this is referring to a redundant robot, right? Okay, so I don't know if Ravi, if you are there in this session. Are you there? Are you there? Is Aarti Ravi Tiwari? Huh? Yes. Okay, so I guess you are there, but can you please unmute yourself and let me know whether this has to deal with redundant robots or not? You can't unmute yourself? Oh, I see. Okay. Okay. In that case, okay, fine. So in that case, your question is it possible to have force control at the tip of one, uh, okay, for a few joints and achieve the different tasks? Actually, really, I don't know the answer, but should be possible because most of the time redundancies can be used to do, most of the time the people use it for position control, okay, or obstacle avoidance, or choose a path which does not hit an obstacle. But there is no reason why you should not be able to, let's say, apply some force at the end effect by the end effector. Okay, because the null space term is, I guess, where are you from, Ravi Tiwari? You are working in DRDO, where? Which DRDO? Okay. So it is possible. I mean, I don't know of any place which has done this. Okay, I need to search, but it should be possible. So if you send me one email, or if you send an email to the TA in the course, we can do some little bit of searching and find out how, if there are any papers where the redundancy has been used to apply a desired force. Okay. Have you looked at this? There is a very famous textbook. There's a very famous textbook. Let me just see. I think Nakamura by basically he discusses all the various techniques for redundancy and optimization. So there's a very famous book. I think the correct spelling is, just 1 minute. Yeah, so I'm going to paste this uh, thing in the Zoom. So if you get hold of a copy of this book, you can see there are many nice ideas in this book. It's an old book, 1990 something. Okay, so you can take a look at this book and see if they have discussed this, whatever you wanted to do. Okay. Anybody else? Which group are you working in, Ravi? You are asking, do humanoid robots can be considered as parallel robot or serial robot? No, it's a answer is no. Okay, because the arm itself is a serial robot, but if the two arms are gripping an object or grasping an object and moving them together, then it becomes like a parallel robot. Okay, so it is never a purely serial or a parallel robot. Okay, so in the robotics group, is there a Pathak there? Ah, okay. So yeah, please tell him hello that he should remember me. Any other question? So Makarand, how are you doing in the assignments? Do you find them okay or not okay? What is the deal?
They're okay, sir. They're a little difficult, but
Oh,
yeah.
what you meant by little difficult?
Some parts I don't get them like immediately, so I have to like watch the videos again and then.
And so once you watch the video again, then you can get it, no?
Yeah, yes, sir.
Oh, very nice. Good. And Ravi, do you find the assignments easy, hard? What is it? Ah, okay. Again, what is little tricky? I mean, you see, this is a proper course, no? So it should be like, yeah, need to choose options carefully. That is correct. You must do that. Okay. Do any of you use Chat GPT?
Sometimes, sir.
And it helps?
Uh, like if you're writing code for some assignments, it helps.
No,
For
no,
the
no, in this course for
no, no, sir.
answering or doing the assignments.
No, sir. No.
Uh, it doesn't help, huh?
No, sir.
But why are so many of your this course persons, those who are doing the same course, why do they insist on using ChatGPT and give wrong answers? Anyway, yeah, the whole idea of this course, at least, that if it is just memory that you see it once and you just memorize and you do the thing, then it is not worthwhile, in my view. You need to at least go back and see the lectures, or you should go back and read the slides. There is no answer or no question which is completely out of the syllabus. So this TAs, and so there are some two TAs. Are you taking help from them? One from ISC and one from IIT Bombay?
No, sir. I didn't ask them for help. I can't
No,
tell
no,
now.
but do you at least have you been to any of the classes? They're doing 1 hour a week every week.
Hmm. Yes, sir. I think I've been told that. So,
Okay. So this is a feedback for us. Whether these TA classes are useful or not, you have to sit in a few and then let me know.
yes, sir.
Ravi, have you sat in any of the classes organized by the TAs? Huh? Nagasudhan, huh? Okay. So there is a Kapileshwar Srikant. He's saying hello. Just out of curiosity, what are the current research in the field of robotics? Would be really good to hear about it. Okay. So, so I can show you a few videos if there are no more questions. There
Hello.
is also, uh,
Hello.
hello, Ravi.
Sir, am I audible? This is Ravi Tiwari, sir.
Excellent. Now you are audible.
Yes, sir. Sorry for that this audio thing, sir.
Ah,
The course is very excellent, sir, and it is
ah,
little bit difficult for us to
ah,
cope up with the slides, sir. I've
ah,
already ordered the book which written by you, sir.
ah,
And regarding the assignment, sir, little bit it is tricky.
ah,
For example, in the latest assignment, one of the
ah,
question was in a model-based computed torque
ah,
control scheme, whether the performance is same everywhere in the
ah,
workspace. In the ideal condition, the answer is yes,
ah,
but in the practical situation, the answer is no.
yes.
So I'm facing difficulty whether to take this option or not. This kind
Ah,
of trickiness is there in the assignments.
I see. Okay. Okay, good. So at least you are made to think a little bit, no?
Yes, sir. Yes, sir.
Hmm?
So based on that only, I'm answering the assignments.
Very good. Very good. So because see, if you put in a little bit of effort now, then you will remember, 6 months later or 1 year later, you will remember that, okay, I had to think about this question.
Yes, sir.
But otherwise, you will forget everything, no?
Yes, sir. Sure. Yes.
Hmm.
And
Okay, there is one more person,
sir,
Kapileshwar Srikant. Just out of curiosity, what are the current research? Okay, I will show you a few videos. Okay, who is Naga Sudha? There is a person by the name of Naga Sudha also. So, and Kapileshwar Srikant. Can you just hold on a minute?
hello.
Just hold on a minute. Okay, so if there are no other questions, maybe I can show you some of the work which is being done in ISC.
Sir, I
Okay,
have one small question, if you
sure,
allow.
go ahead.
Sir, here, this for brief, I'm just working on the exoskeleton system. So there, I just wanted to know the how the compliance,
Ah,
which is added to the link, can be utilized for the better control of exoskeleton. Because if you can see, the exoskeleton is coupled with the human body, and the human
yes,
body is having its own compliance.
yes.
So, is there any particular or good method which can we can adopt?
I don't know the answer
Okay, sir.
because see, normally, uh, rigid robot is the easiest to control. Okay, that doesn't mean that you cannot control compliance or you cannot, control flexibility in a robot.
Sir.
But it is always much harder.
Okay. Yeah.
It is always much harder.
Mhm. Okay, sir.
So are there any other questions?
No, sir. Thank you.
Okay, so one of the participants wants to know what kind of work we are doing here. So here is, I will show you a few videos. This is just a sample. Okay, just let's try it. Let me just see how to share. Can people see my screen? Huh?
Yes, sir. It is visible.
Okay, good. So here is one of the research work which is going on. It is being done by a student here. He is also one of the TA. So this is the robot. It's a quadruped. So if you watch the video, this was done about 6 years back in the lab in the our department here only. And then now this is after a few 1 or 2 more years later, this was done using another robot, four-legged quadruped. This shows the design of the quadruped, how to simulate it, and Huh?
Yeah, okay, sir. In between, it got cut off.
Huh? Or little thicker. Yeah, that happens. Yes. Okay. So this is one area where we are trying to build a four-legged robot which can do various kinds. So it can do gallop, it can do trot, it can do bound, it can walk. These are little old, some 2, 3 year old, maybe 3, 4 year old video. If you go to this lab, which is called STOCKCH lab. Hmm. Okay, where is the, just 1 minute. Okay, if you go to this lab, let me just give you the link. So can you still see my screen?
Yes, sir.
Okay. So what you could see was there was this robot which was trying to walk around in the campus, and even the dogs were fooled, or dogs were curious. Okay, and all of these you can find it in this website. I have put it on the this thing. So as you can see that there are these dogs which are looking at it, they don't know what to think of it, whether it is real or imaginary. And this robot can walk over cobblestones, it can go over green grass, it can even walk in uneven terrain.
So, do it have a foot sensor also?
Yeah, I think that there are no foot sensors right now.
Okay, sir.
There are motors. There are 3 motors in each leg. One at the knee, one at the hip, and one to the other direction, perpendicular to that direction. 3 of them are there. And so there are 3 into 4, 12. So this is supposed to carry some camera and various things, and it can go to various places and then see. Okay. So this
Okay,
is
sir.
one example. I don't want to switch off everything. Okay. Can you see this?
Yes, sir.
Okay, so this is another research topic which one more TA here he is working on. This is basically what are called as cable-driven robots. Okay, so what you can see in this sort of semi-transparent thing is there is a backbone, this white backbone, and on the backbone there are these discs. Okay, and these discs in the disc there are holes. So through these holes, one cable or a wire is connected from one end to the base. So, and there are these motors at the top which you can rotate, and then it will pull the wires. So depending on how you pull it, this whole backbone will bend. So what here it is showing here is that you can uh, pull the wires. There are 3 of them, so it is like a 3-fingered gripper. And then when you pull these wires properly, you can grasp the object, which is in this case a polystyrene cube, and you can rotate it. You can move it in directions X, Y, Z, and you can rotate it. So the advantage of this gripper as opposed to any other robotics gripper is these are very, very lightweight. Okay. They are lightweight. Secondly, they can grasp uneven shapes. So right now it is showing that it is grasping a nice cube, but you can think of it that, depending on how you pull, you can go and grasp a surface or a sphere or some other shape properly.
Sir, when you say it depends on how we pull the cable,
Ah,
so basically it is a combination of 3 cables, if I'm
yes.
correct. Okay.
So actually there are 4 cables. In one of them there are 2 and the other ones have 1 each.
Okay, sir. So, sir, can be extended for higher payload?
Yes, not higher payload.
Sir.
That then you have to make this backbone stiffer. You have to make this cable stronger, and then you have to make this discs also different.
Okay, sir.
Okay. So this is another one which you can see. Okay, let me show you one more. This is a slightly older one, but this is what is called as a snake robot. Okay, so there is a center for AI and robotics here in Bangalore, and they have a very good robotics lab. And what they were interested, and one of my PhD students some time back, this is again 5, 6 years back. So you can see that this robot, which has all these small, small links, and there are these motors. So if I want to stop it, so it is on wheels, but each of these black thing is like a motor. Okay, each of them are links, and they are connected by together by means of motor. And then there are all these wires which you can see, which is bringing current and some desired rotations from somewhere. And I'll show you where it is coming from. Okay, so there is a student who is walking with a laptop. You will see a little bit very soon. You will see the person, okay, his legs. And what he is doing is in the laptop, he is doing all these calculations. Basically, what is the calculation? How much each joint of each link should rotate such that it will go in a path and not hit any of these obstacles. Okay. So this is a very nice problem. So if you see a snake which is going through some obstacle field, it will move such that wherever it is close to an obstacle, only that part of the body of the snake will change shape, whereas the tail can still be straight. Okay, or once the head has cleared the obstacles, the tail will try to avoid the obstacles, but the head will continue to go straight, or whichever is the path. So that is exactly what we are trying to show here. And all those computations are being done by in a laptop, which the student is carrying. The commands to the motor to rotate in the correct way, such that it will not hit all these obstacles, is coming, and then you run it. So there is no sensor as such right now. So conceptually, you can have a camera which this snake robot is carrying, and then it can find out, oh, I am so far away from the obstacle. So let me move whatever is the current theory, which is our current algorithm can be implemented then online and on the snake itself. But right now it is not happening. Right now, all the obstacles are known. The computation is done offline, and then the data is being sent. So let's look at this video. Huh? So this is also shown in week 7. Okay, so as you can see, there are all these pieces of plastic, rings and other things which are lying there. And this robot is able to avoid all of these and still move through this field. You can now think of many, many applications for something like this. So for example, if you have an earthquake, if some earthquake or something is happening, and you can send this snake robot, of course, this is plain, but similar ideas can be extended for 3D. You can send it through this obstacle strewn, place, and it will go through the place and then take pictures and tell you if there is anything alive or not. Okay. Just show you one more. I don't think it is here. Okay, this one is also reasonably interesting. So this is how many of you know what this is, what I'm showing?
It is a medical device, sir.
Yes. Okay. So this is called as a laparoscopic surgery tool. So basically, let me just show the video and then I'll show you again. So what you can see here is that when you rotate this, there is a joint here which will bend. So it is like a wrist. Okay. And also there is this another rotary joint which will rotate this end effector. So in this case, the end effector is a scissor. Okay. And there is also one more finger here where you can grasp or you can cut an object using the end effector. So this is a very sharp scissor. So now let me tell you why this work was done. So most of the time, okay, most of the time, this is what a laparoscopic tool is. So you can close and open this end effector. You can cut something or you can grasp something. Okay. And you can also rotate it and you can go in and out. But there is no wrist like the one which I showed you here. So in this case, not only you can go straight, but at the end you can go left or right. It's very similar to a robot wrist. And the advantage of that is you can go around obstacles. So when you are doing some surgery or you are doing some sample collection inside your stomach, okay, then you can go around an obstacle. So it is much, much easier to do this. So we had applied for a US patent, and after a while we just gave up. But there is an Indian patent for this device. Okay. So stop this. Okay. I wanted to show you the sun tracking, which I don't know where it is right now. I can't find it here. Huh? Huh. Yes. Yes. This is one more which I want to show. Okay, just let's watch the video first, and then I will describe to you what it is doing and what is the novelty and what is the research here. Okay, so let's start again. So what we have here is, I'm going to pause this. So what we have here is what is called as a heliostat. And what is a heliostat? Basically, it's a mirror. Okay, and the mirror can move about 2 axes. So it can track the sun when the sun goes east to west, and it can also track the sun during seasons, it goes little bit north-south, right? Everybody knows that, which is why we have the shortest day and the longest day. So it goes from Tropic of Cancer to Tropic of Capricorn, so plus minus 23 point so many degrees. So what we have is this mirror, which will track the motion of the sun, and while tracking, the normal to the mirror is located in a way such that the so the incident beam of the sun is reflected onto this receiver. In this case, this is a tank on top of one of the roof of the building. So, and what is the idea? The idea is that if you have many such mirrors and you can project the incident beam of the sun into this, so you can think of what will happen. Suppose you have 1,000 of them, okay, in a field. So what do you think will happen? So what do you think will happen if I move these mirrors such that it is always pointed at this one place? And you have thousands of mirrors. Okay, anybody want to take a guess?
We
Sir,
can use
Yeah, go ahead. So what will happen? Huh? I know it was there in the lecture also. So my TA is telling me that you have not listened to my lecture also.
no, sir. The directed beam can be used to for some other energy conversion, sir.
Yes, you will get very high temperature here. Lot of heat is being concentrated here. Okay, so that is the thermal part. Let's not worry about thermal part. So what I'm trying to tell you is this mirror has to be moved about two different axes. Okay, one north-south and one east-west. Okay, so in robotics, what would be the words used? If you want to explain to a robotics person, this is what we are doing, what will you tell?
Normal and tangential direction.
No, any other? These are two Euler angles,
Okay, yes, sir.
right? So let's say one of them is the x-axis, other one is the y-axis. You have to rotate about x and y, okay, like two Euler angles. Okay. And also, in this case, the z rotation is not there, but this is a 2 degree of freedom device. So there are two motors which will ensure that you rotate about these two different axes, two orthogonal axes. So the left picture here is that device. So if you look carefully, there is a motor here and there is another motor here. Can you see my cursor?
Yes, sir. Yes.
So one motor here, one motor here. So this motor will rotate in this direction and the other one will rotate about the vertical. Okay. So this is a serial robot, serial heliostat, 2 degree of freedom, and it is reflecting the beam here. We also made one which is a parallel robot. It's a 3 RPS robot. Again, it is there in the lectures. And what is the advantage of a parallel robot? That this mirror is now supported at 3 points. Here, the mirror is supported at 1 point only. And hence, the load is shared. So this 3 RPS robot, again, as mentioned in the lecture, and here you can at least see clearly and think clearly that it is it has much more stiffness. It is much more stronger. So I can carry a much bigger mirror without doing anything to this in this case. So first thing to show is that this 3 RPS will also track the sun, because I mean, what is the point in making something which it doesn't serve the primary purpose? We know this 2 degree of freedom tracks the sun. This 3 RPS should also track the sun. Otherwise, there is no point. Okay. So what you can see here is the one image is here, one image is here, and as the day progresses, you will see these images move, and then you will see that it is always focused at the top of the thing. So sometimes it is very close, sometimes it's a little far, and any guess why it is happening? Like this is more or less merged. This is what we would like. Why do you think that is happening? Any guess?
Maybe sir, manufacturing errors at the
Yes,
joints.
yes, exactly. So these are all student-made projects. Okay. So there was a PhD student who is now in UK. He made this. He made this parallel heliostat, which is to track the sun. Okay, and he showed that okay, I have one which is a existing normal one, and this here is a new one. Both are doing more or less the same thing. Some small errors are there, and that is a good enough PhD research on a thesis topic. Okay.
Yes, sir.
And there's a lot of theory. So how much should I move these prismatic joints each time so that that angle of incidence is equal to angle of reflection and the normal is pointing in that direction and so on. The basic problem of tracking anything. Okay, so this was also there in the one of the lectures, and I hope if you haven't seen it, if it's I'm repeating it once more. Okay. This is the work being done by uh, Pramod Pal. So let me just show you this demo directly. I don't know whether this is not there in the lecture something. Can you see this?
Yes, sir.
Okay. So this is also there in the dynamics module. So some
Yes, sir.
simulation results of a end of a 2-hour robot going up and down about a y-axis is shown. Okay. Here, this is the actual hardware. So what I showed you is this, I want this tip to go along this vertical, okay? And you set this controller gains in some way such that it does that. So it is doing okay, but it is still okay, not too bad, but it is still oscillating a little bit. And that is the whole thing about control. You have to try it out. So whereas one of the first thing that the student did was this. So now it's really, really not good, right? As for this is for a different controller gain. There are two motors here, one at the base, one here, and you have to set the controller gains for this motor so that it goes in this. And what I'm trying to show you here is that you have to do a lot of trial and error. Okay, you have to do a lot of simulations. You have to do a lot of experiments before you can come to this. So this was initial, and now you can see it is so much better. Everybody agrees?
Yes, sir.
Okay, so in robotic control, it's although theory is there, you can get some numbers from theory, but eventually you have to do experiments because everything cannot never be modeled in a theory in MATLAB or any other software tool that you are using.
Sir, is it possible to get the this model, mass model, and Coriolis matrix through experiment?
Yes and no. Yes. So that is again, uh, there is this whole field, okay? There is this whole field called adaptive control,
Okay, sir.
okay? And in adaptive control, the basic idea is that you have some idea what is the mass matrix, but you may not know all the terms exactly. You have some idea about friction and gravity and various other terms, but you don't know them exactly. So this whole theory was developed in the 80s and 90s and earlier, okay, that you can use the output of the controller. Well, you can use whatever is the error between what you want and what you are measuring to change the parameters of the model. Okay, so you change the parameters in a way such that the errors decrease, and that is called adaptive control. So that is one way of doing it. This is a classical way. So right now, nobody does that because right now you just feed in this data-driven control. Okay. How many of you know this data-driven AI, ML, reinforcement learning, all these new buzzwords?
Yes, I know these words, but never used, sir.
Yeah, I also haven't used it. Okay. So, but the whole idea in these newer ways of doing it is you give lots of data. So you tell that this is what I want. Okay. And here is some values of mass parameters, some values of controllers, some model parameters, and then you let it do. So if it is not doing properly, so for example, that quadruped falls down, okay, then you have an algorithm which will say that now don't change any of the things such that it falls more. So you reward the system such that it falls less. Or in this case, you reward the system such that the error decreases. Okay. And then you change the model parameters, you change the controller gains, you can do many things. And then after all these data, actual data, once it is fed into this program, then most of the time it will learn what are the parameters, what are the model, and then it will work much better. Okay, any other question on this? So here is one. I showed you that obstacle avoidance, no? So I had a master student once. He wrote this program where it is a simulation. It is not a real life thing. It is showing how an endoscope can go into the stomach region to go and take pictures. At the same time, it will not hit any of the obstacles. Uh, Anybody know what is an endoscope?
Yes, sir. For inspection inside the
Uh,
liver.
uh, GI tract inside your stomach. So, so there was this problem given to us by a doctors that if you want to train uh, new surgeon or new endoscopic person, how will you train? You have to have a very good CAD model. You have to have a very good, imaging, such that when you're putting it, this thing is going through. And then if you're not doing it correctly, it will do all kinds of things. So so what this student did was initially that he showed how you can simulate the motion of an endoscope. It is sort of going through the mouth and then it is going through this GI tract. this GI tract is a real life GI tract. Okay, this is how relative sizes and length of the stomach and your food pipe is. So this is the stomach and this is the food pipe. Okay. So there is this data is available in the internet on how does a GI pipe look? 3D model. So this student implemented an algorithm of very similar to that snake robot which I showed you. But in this case, now the snake robot is not moving in a plane and avoiding obstacles. Here it is going through this tube and making sure you don't go and scratch the sides of the tube. You don't go and hit something else. Okay. Okay, so I think I'm speaking for a long time. Let me stop this and let's go back to if there are any other questions from anyone here. Okay, any other question? It's almost 1 hour. I think we need to stop soon. So here is your chance to last chance to ask questions today. Huh?
That was my question.
So if there are no questions, can we close?
Yes, sir, we can, sir.
We can close, no?
Yes, sir.
Yes,
Thank you, sir. Thank you.
About
Yes, sir.
almost 1 hour is over, so we should be able to close anyway. No? Okay, so if there are any questions, you can send email also.